This is part of our video series on human-centered evaluations for NLP explanations. Check out the link for more resources. You're currently here. Welcome back to our explanation of explanations. In the previous video, we talked about uncertainty estimation, and now we're going to actually highlight stuff with a new form of explanation.
That form of explanation is called input attribution, where the prediction is attributed to some important words in the input. We often use a heat map to visualize it, where darker color corresponds to higher importance.
So what counts as an input?
For our running example, legal entailment, this could apply to both the context and the statement. But for the rest of the video, we'll just talk about how we can generate the heat map for the statement.
Okay, now I can see what words are important. First, whether the case is administrative or not is important. The negation not is important. And then the phrase, he who decides must hear, is also highlighted, indicating that it too is important.
And you can combine this with the model answers yes with 92% confidence. A lot better, right?
Absolutely. But you just kind of threw the highlighting up there. Where did that come from?
Good point. Let's see how we can generate the heat map. I'll abbreviate the context since we're generating the heat map for the statement. Let's think about it this way. What would happen if I remove the word not from the statement?
Well, then the statement would be the rule of he who decides must hear does apply to administrative decisions. The system should say that it's not entailed.
And it does. The model changes its prediction to no with high confidence. This gives us a way to compute the importance or attribution score of the word not.
So if a word, when it's removed, changes the confidence a lot, it must have been important for the original prediction.
Exactly. Here, the confidence after the removal is 98% for no, which means only 2% probability is assigned to yes. So the confidence difference and the attribution score is 90%.
Can we see that for a different word that isn't as load-bearing? How about who?
Removing it only slightly decreases the confidence, so it gets a lower attribution score, 22.
Okay, so we talked about the importance of individual words. How does this lead to the heat map that we talked about before?
This method is called leave one out, which means you leave one word out of the input every time and repeat this process for every single word in the input. Then you compute an attribution score for every single word. You can collect all these words and apply normalization if you want, and this gives you the scores to generate the heat map visualization that you saw earlier.
Removing the word not reminds me of counterfactuals. You're asking the model, how would you predict if the word not wasn't in the input?
Yes, exactly. And counterfactuals aren't limited to removing words. You can also replace them.
So I could just replace the word administrative in the statement with judicial and see how the prediction changes? How does that explain what's going on?
The context explicitly said that the rule does apply to judicial decisions, and the model correctly answers no. Earlier in leave one out explanation, we saw the whole phrase administrative decision was highlighted. But now we see it's the word administrative that's doing a lot of the work. And you can consider more subtle changes to the input, such as swapping the words and changing the statement to be about he who hears must decide, instead of he who decides must hear.
So how is this better than leave one out?
Unlike input attribution, which only gives you a sense of how sensitive the model is to the appearance of each word, counterfactual explanation provides additional information about the model's decision boundary.
So the decision boundary is where it goes from positive to negative. How does this help us figure out where that is?
For instance, you can add a negation to every single example and see if the model always changes its prediction. This will give you an idea about whether the model can understand negation correctly.
So how do you generate counterfactuals? How could you come up with these perturbations? And leave one out, we use a brute force method. But that's fine since we only have a small number of words in the input. But it wouldn't be feasible to spell out all possible perturbations specifically if you allow insertions, right?
And only a very small percentage of all possible perturbations will give us valid input sentences. And an even smaller percentage of those will be relevant. For example, if we replace too many words, that might be too disconnected from the case that we're considering here.
I see. But then it seems like we just have to rely on human judgment to define the space of valid perturbations?
Yeah, and that's why many of the counterfactual datasets are constructed using a human to find a small change that can flip the model prediction.
That reminds me of adversarial attacks.
Yes, and the underlying methods are very similar. You can use an adversarial model to guide humans, or you could also limit your space of brute force search and use a language model to filter out the majority of invalid perturbations, and finally ask a human to verify those counterfactual examples.
Okay, so that's what you meant when you said the explanation method could involve a second model. All right, and that's enough for one video. We've talked about a variety of explanation methods so far. We've talked about uncertainty estimation, input attribution, and counterfactuals. In the next video, we're going to talk about some of the limitations of these approaches and where explanations might go next. This video isn't the end. You're currently here. If you're lost, click on the link below for source code, slides, and other resources.